Alright, so we can not only create standing waves on strings, we can also create standing waves in a tube of air. So this is a longitudinal wave that gets formed in a string, and this is basically how every wind instrument you can think of works, whether it be a trumpet, a trombone, a clarinet, a saxophone, a flute, basically creating standing waves in the air. So there's basically two types of tubes that we deal with. A tube that's open on both ends, or a tube that's closed on one end. We can think of instruments that look like both. Something like a flute really is a tube that's open on both ends. Something like a trombone or a trumpet is really a tube that's closed on one end. If we actually were to look at the organ in the chapel, what you'd see is that there's some of those tubes that are open on both ends and some that are closed off on one end, and they create different frequencies. So let's first of all look at the tube that's open on both ends. So in order to get a standing wave, something that's going to create sound, we need to have the antinode, or the place where there's constructive interference, on the outside ends of the tube. So here is the first frequency where that would be true. We have one antinode in the middle and one node in the middle and two antinodes on the outside. The second time we get is if we put an entire wave inside the tube. So now there's antinodes on the outside and one in the middle and two nodes on the inside. And we can see what happened if we go to the third, the fourth, and the fifth. Basically what we're doing is we're adding more waves inside there. What's true about the wavelengths of these waves is the wavelength of this wave is twice the length of the tube. The wavelength of this wave is just the length of the tube. Wavelength of this wave is 2/3 the length of the tube, because there are 3/2 of a wave in here. Here there are two full waves in there, so it's half the length of the tube. And here there's 2.5 waves, so the wavelength is actually 2/5 the length of the tube. So I can use this information in order to figure out how does this relationship actually work. Well, velocity is equal to wavelength times frequency. I could say frequency is equal to velocity divided by wavelength. And so what I end up with is the fundamental frequency. The lowest frequency is V over 2L, then V over L, then 3V over 2L, then 2V over L, and then 5V over 2L. If we actually simplify this relationship down, we can get the fundamental frequency looks like some number n, so 1V over 2L, 2V over 2L, 3V over 2L, 4V over 2L, 5V over 2L, times V over 2L. Thing to point out is for the tube and open on both ends, the equation for a standing wave for a tube open on both ends looks exactly the same as the equation for a standing wave on a string. Now let's look at what happens if we close the tube on one end. And something interesting happens when we close the tube. And the thing that's interesting that's happened is if you have a sound wave that comes down the tube and bounces off this closed end, what happens at this end of the tube is the sound wave reverses polarity, or reverses direction. This is a phase change and it becomes inverted. So what that means is if you have a crest hitting this end of the tube, it actually reflects back as a trough. So there's always a location of destructive interference at the end of the closed tube. So in order to have sound come out of the end of the open tube, you have to have an area of constructive interference. So this is the first time that happens. And it happens first when 1/4 of the wave is inside the tube, so the wavelength is 4 times the length of the tube. The next thing is 3/4 of the wave is inside the tube, so the wavelength has to be 4/3 the length of the tube. Here, really 5/4 of a wave is inside the tube, so the wavelength is 4/5 L. And here 7/4 of a wave is inside the tube, so 4/7 L. So if we look at what the frequency is by using the same equation we had before, we get V over 4L, 3V over 4L, 5V over 4L, 7V over 4L. And what we find is that the equation for closed tubes looks like this. NV over 4L, where N can be any odd number. Has to be an odd number. Now I've seen this equation written other ways so that N could be other numbers, but I would actually consider this to be the first harmonic, the third harmonic, the fifth harmonic, and so on. So let's do a quick example problem. I have a tube with a cap on one end but open on the other end. Has a fundamental frequency of 130.8 hertz, and the speed of sound is 343 meters per second. This is really a tube that's closed on one end. If the cap is removed, what is the new fundamental frequency? And then what is the length of the tube? So here are the things that I know is that the frequency for being closed on one end is 130.8 hertz. We know that we're fundamental, so n equals 1. And I know the speed is 343 meters per second. Here's some things that I don't know. The length of the tube or the frequency of the fundamental for the open on both ends. Two relationships that I have is the frequency or how closed tubes or how closed tubes act and how open tubes act. Similar equation, just a 4 versus a 2. So the first thing I'm going to do is find L, because I have enough information to figure out what L is right away. I can multiply 4L over to this side, and then I get 4L frequency of closed tube. And then if I divide by 4 frequency of closed tube and then substitute my numbers in, 343 divided by 4 times 130.8, I get 0.656 meters. I could then use L to find frequency of the open tube. And what happens when I plug in all those information, 343 divided by 2 times L, I get 261.6 hertz. The other thing to look for to make sure does this make sense, well, if N, V, and L are all the same, and there's a 4 and a 2, this one should be half as big as that one. So if you take 261.6 and divide it by 2, guess what you get? 130.8. So that seems to work. So that's how standing waves work in tubes or with air, and how we can use interference to begin to describe really how most wind instruments operate.